you had to be a good breezy and change your predictions after...
Guillaume Baudart, bienvenue sur Learning Bayesian Statistics.
Thanks.
So, I'm very proud because I am increasing the quota of French people on the show. So this is good. We had a really recent one with Nicolas Chopin. It was episode 82. So yeah, the French community is making its way slowly but surely on the podcast. I'm pretty sure some people are not happy with that, but that's okay. So, Guillaume, yeah, super happy to have you on the show. I want to thank Virgile Andreani for putting us in contact. So Virgile is a fellow PyMC developer. He's also working with us now at PyMC Labs. So it's really cool that he made that connection between us two because, I have so many questions for you today. And I think it's going to be an original episode because a lot of the things we're going to talk today, I think I've never really covered them on the podcast. So that is perfect. So thank you, Virgile. And now, without further ado, let's dive in and, as usual, start with your origin story. Guillaume, how did you come to the world of statistics and probabilistic languages, and how sinuous of a path was it?
So first, thank you very much for having me. I really enjoy the show, so thank you very much. And to answer your question, it was definitely not a straight path. So as a kid, I just wanted to do music, and then for some reason, I went to science and math, and I did a straight French curriculum in math and computer science.
Mm-hmm.
And then during my master, I tried to reconcile these two aspects. And I did a master in computer science, signal processing, acoustic, everything in science applied to music, basically. So it was at IRCAM, which is a small part of the Pompidou Center that is focusing on music and modern art.
Mm-hmm.
And so during this year, I played a little bit with machine learning, Gaussian mixture and stuff like that. And I was working on this project called Antescofo, which is a music score follower, where basically you have live instruments that try to play with electronics.
Uh-huh.
And this was the first time I saw some Bayesian methods, because the score follower, the things that was trying to see where the instrumentist was playing in the score, was implemented with some kind of particle filter or a Kalman filter. So I saw these vague notions, and I remember discussing that with a friend, and then I stopped, and I did a PhD on a completely different topic, which was on embedded systems. And at the end of my PhD, I was hired by IBM Research.
Mm-hmm.
And after a few years at IBM Research, they asked us to look into probabilistic programming, because they said, "Hey, looks like it's a hot topic right now.
Okay.
It could be interesting for us. So can you take a look?"
Mm-hmm.
And this is where I started to actively learn about probabilistic programming, Bayesian method, and stuff like that. Starting from the very basic, the survey paper. The first paper I read was the Andrew Gordon and co-authors, that is called Probabilistic Programming.
Mm-hmm.
It was published in the Future of Software Engineering tracks at IXI or something like that. So yeah,
that's nice.
And after a while, we were working mostly with Louis Mandel, and we had a similar background in embedded system and reactive programming.
Mm-hmm.
And we had this idea that maybe we can combine probabilistic programming with reactive programming and see how far we can go. And this was the beginning of ProbZelus, and still actively working on that.
Okay, nice. I didn't know about that background story. So, and what kind of music were you into? What was your dream, ideal career path? in music?
Oh, for me,
Yeah.
right. So, depending at what age, right? So,
Yeah.
when I was very little, I wanted to be a solo violinist, and
Oh,
then
okay.
you quickly realize that you are not good enough.
Mm-hmm.
That's a good part with violin. Um, and so then later, I really wanted to do applied science around music. I built some stuff for musicians and things like that. And then I got more interested in the science part and programming languages and semantics and stuff like that.
Hmm.
So
Yeah, this is so nice. Yeah, I mean, I understand. Violinist. This is quite cool. Yeah, always extremely impressed by this instrument and the ones who are able to play it
yeah,
so masterfully. Um,
I mean you
and
haven't heard
also,
me play it yet.
yeah, and also, I mean, the connection between math and music is actually quite close, right? Even though I would think that if you take some random persons in the street, they would not necessarily make that connection very fast. But it's something that I often say that like, music is actually very mathematical, and that all kind of translates the beauty of math
Yeah,
in a way.
yeah.
So cool. Thanks. I have a better idea now. And so I think you already kind of answered that, but maybe let me ask you more formally if you remember how you first got introduced to Bayesian methods.
Yeah, so the first encounter was this score following systems where you try to align a score with a live
Mm-hmm.
musician, and you have some priors about. I mean, the priors is basically the score, right? Where
Uh-huh.
you expect the musician to be, and you have an estimation of the tempo, the speed at which the musician is going, and you want to, based on observation, so the sound that you actually hear, you want to align the score with
Ah, okay.
the live performance. So that
Nice.
was
Okay. Yeah.
the first system.
Yeah, very Bayesian indeed.
Yeah.
Um, and so you have an interesting work, but for me it's hard to define it. So how would you define the work you're doing today and also the topics that you are particularly interested in?
Right. So right now, so I'm back in France after a few years in the US at IBM
Mm-hmm.
Research, and I'm in an Inria team that is working on reactive languages for embedded systems. So
Mm-hmm.
the idea is how you design your embedded systems and then build the entire compilation chain so that you have strong guarantees on the code that executes on your embedded systems. And we
Uh-huh.
are targeting like a critical embedded system like airplane controller or things like that. Where you really want to be sure of what you're doing. Um, and on top of that, I want to add Bayesian inference. So I want embedded system designers to be able to write their own probabilistic models
Mm-hmm.
and use that as part of the design of their system. And
Okay.
so the interesting part is that you can use that. There is two ways to use a probabilistic model. You could use
Mm-hmm.
that to simulate your environment because you have an open environment. So it's always useful to have something that give some uncertainty. But you can also use that inside the system. And the classic example is that you want to implement a tracker for your position. You want to estimate your position from noisy observations.
Mm-hmm.
So the classic way to do that in embedded system is to manually code some stochastic controller or some stochastic method, say a Kalman filter, for instance.
Mm-hmm.
Um, but what we want to do is to give the programmers the ability to write the underlying probabilistic models with all the uncertainty everywhere and
Mm-hmm.
leave the compiler and the runtime do the hard job for you of computing the solution.
Mm.
So this is why we are trying to develop ProbZelus. And of course, ProbZelus is just an academic prototype so far, but this is
Mm-hmm.
the long-term goal.
Ah, okay. Okay, yes. So that's a bit clearer. So actually, yeah, let's dive into ProbZelus and can you give us an overview of ProbZelus and its significance in the field of programming languages?
Yeah. So ProbZelus is a synchronous language that is extended with probabilistic constructs. And first, I would like to mention that this is a joint project with a group at MIT, so the group of Mike Carbin at MIT, and most notably Eric Atkinson and Ben Sherman at the beginning, and then Charles Wan and more recently Eli Chen, who are working with us. And so maybe I should start by describing what a synchronous language is.
Yeah, for sure.
So the idea is that you want to program with streams because you want to program systems that will never stop, right? So you can see your system as a stream processor. Everything is a stream. So instead of 42, you have 42, 42, 42 all the time. And everything is based on a discrete notion of time. So at each time step, you compute a new value for all your variables in your program. Okay. And so you compute streams of values that we sometimes call flows.
Okay.
And you build your block by assembling these stream processors, right? And this is so for control engineers, there was this notation that was called block diagrams, where you could compose these blocks together, and in each arrows you have a stream, and each block is a stream processor. And so it comes from that. And the core idea of synchronous languages, which are a very, very French notion, like synchronous languages were introduced in the 80s by 3 teams in France concurrently. And the idea was to restrict what you could express in the language, such that you have a very precise formal semantics for the language, and you can have a compilation chain that gives you a lot of very good guarantees on the code. And the main guarantees that you are looking for is execution with bounded memory. So you are guaranteed that whatever you do, you will never blow up the memory, which is useful because the system never terminates again. So it should be able to keep running and running and running. So this is synchronous languages, data flow synchronous languages. And on top of that, we want to add the classic probabilistic construct. So you want to be able to sample from a distribution, and you want to do some conditioning. So observe a variable from a distribution. And then you want to infer the posterior distribution from higher Z observer. And so if you think about the difference with general probabilistic languages, now what you want to do is to infer a stream of distribution. So at each time step, based on some observation, you want to output posterior at a given time step. And a key property of ProbZelus is that you want a reactive system. So you want to be able to interact with intermediate results of the inference. And this is different from most probabilistic languages where you have a bunch of observations and you want to compute the posterior and you can throw away intermediate results. Like you don't really care. Here we want to observe them and potentially we want to react to what we've seen, which might change future inference. So if you think about a tracker, for instance, you are estimating your position, and based on this estimation, you can take one direction or another, which would change the next observation. And so, so we call that inference in the loop, and this was something that was really at the heart of the design of the language. And then to talk a little bit about the inference, so we have this language that is a bit weird, and then we had to come up with an inference algorithm that would work with all these constraints. And we ended up using sequential Monte Carlo methods that you talked a lot with Nicolas Chopin in a previous episode. And this was because exactly for what I just said, is that you get access to these intermediate results. And so this makes sense. And so we were able to build the first prototype with basic sequential Monte Carlo, like a basic bootstrap filter, relatively quickly. And we were really happy that it worked. And we focused on the semantics for a while, and this was a little bit tricky. But then, like Eric and Ben, they read this paper in Sweden, I think, which was about automatic Rao-Black realization of sequential Monte Carlo method. So the idea is that you want to do symbolic computation as much as possible because like a basic particle filter doesn't scale really well and the performance are not that great, especially for big models like and there was this paper that was called I think automatic Rao-Black realization something by Lawrence Murray and Daniel Duden and David Broman. And the idea is that you have this runtime that is trying to do symbolic computation as much as possible, so trying to apply probability theory as much as possible, mostly conjugate priors rule. And when that fails, you fall back on a particle filter. So you sample some of the variables and you try to keep on going like that.
Okay.
And the design of this inference of this algorithm for ProbZelus, because we wanted to adapt this algorithm such that it would run in bounded memory. So this was the first. This made the first true prototype of ProbZelus.
Nice. Okay. And so, and to be clear, so we'll put the GitHub repo, of course, in the show notes of ProbZelus. And what do people who are interested in this, how can they run it?
Everything is open source, so it's on GitHub. So you can find the prototypes. There is a bunch of examples and a bunch of benchmarks also if you want to try that. You do have to get used to the syntax, so it's probably easier for people who are familiar with OCaml. So everything is written in OCaml. But you can try it. There is no need to install anything apart from OCaml and ProbZelus.
Yeah, nice. And do you need? Are you at a stage where you need some people to come in and do some pull requests, or are you still at a very early stage of the development?
I would say we are in the middle of that. So it's not like the repo is not really polished in the sense that there is a lot of missing stuff in the doc, and it's mostly, as I said, an academic prototype, but it's always nice to have pull requests and contributors. So if people want to take a look, please do.
Nice. Yeah, so folks, we'll put that into the show notes, and feel free to check it out, and we'll then send some pull requests to the ProbZelus team. And oh yeah, actually, so you talked a bit about like the different advantages that ProbZelus would offer, especially if you're working on that kind of topics. And before we dive a bit more into that, because this is a very technical use case, so I would be interested if you could explain a bit more now. Something that I've read in preparing this episode is that so there's this concept of synchronous languages that you talked about, probabilistic synchronous languages, which is ProbZelus. And I saw that it relates to hybrid systems modeling. Right. So can you talk a bit about that so that listeners get a better idea of how and when these languages would be useful?
Right. So as I said, like synchronous languages and data flow synchronous languages. So the original language for that was called Lustre or Luster for English speaker in the 80s. And then more recently, there was a lot of work by Marc Pouzet and Timothy Bourks and co-authors about the programming language Zelus, which is also a synchronous language, but that was extended with dynamic, like continuous dynamics. So the idea is that you want in the same language to write your discrete controller using your data flow stream processors, but you also want to simulate an environment, and a physical environment is typically described with ordinary differential equations. And so Zelus was a huge effort to be able to do everything in the same language, and you could then the compiler would separate the part that talked about the environment and the part that are the discrete controller, and link with ODE solvers and run the entire simulation. So what you have in Zelus is that you really have a full synchronous language in the classic sense, that is discrete time and with stream combinators and stuff like that. But you also have continuous dynamics. And ProbZelus is focusing only on the discrete part so far, because it was already hard enough to extend everything and to do the language design. But this is also a long-term goal. Can we reconcile the two worlds, like probabilistic programming on one hand and continuous dynamics on the other hand? So we played a little bit with that, and I think if you look at the repo, there are some examples that are already there. But it's really toy examples, like you launch a bouncing ball, and you are just listening to the tick that does the ball when it rebounds, and you are trying to compute the gravity based on that.
Ah, nice.
And so this kind of toy.
Ah, okay, nice. And so this kind of example would be what you would describe as a hybrid system.
Yeah, so basically you embed an ordinary differential equation inside the probabilistic model. And so, another way to see it is that you, like for probabilistic programming in general, what you're describing is a generative process. And for this generative process, you need to solve an ordinary differential equation. And so, it's
which is usually very
problem.
Hard.
Yeah. And so we are right now for the toy example, we limit ourselves to very simple inference algorithm for one, and we also limit ourselves to a particular kind of differential equations where you just, like, the probabilities only occurs on discrete events. So you don't have, it's easier to explore this.
I see. Okay. Yeah, because ODEs are usually really nasty to infer, right? At least in the Bayesian framework. I don't know in other frameworks, but at least in the Bayesian framework, it can get very nasty to estimate.
Yeah, so that's why I said it's a long-term goal. Like we played around, and there is everything that you need in the language, like for a programmer point of view, but there is everything to do for the runtime and the compilation.
Yeah. I mean, I've talked a bit about that. We've had Dimitri on the show. I don't remember the number of the episode, but we'll put that in the show notes. And also Adrian Zabelt, episode 74, if I remember correctly. Adrian created a Python library called SunODE that plays well with PyMC, of course, because Adrian is a PyMC dev. So I'll put that in the show notes also. I know Adrian does a lot of work on that, and he's usually very keen to work on very hard mathematical problems. So if he's working on that, you can be sure that it's because it's interesting mathematically. Maybe can you just sum up for the listeners why ODEs are so hard to infer for the Bayesian framework?
Right. So in general, like from a mathematical point of view, I'm not sure I have anything interesting to say here, but for our prototypes, you can imagine that you have a particle filter. So the way you do inference is that you simulate a bunch of parallel executions of the same generative process, and you accumulate all these particles, and that gives you an approximation of the posterior distributions. And if you think about the ODEs, you need to solve the ODE, so you need to embed one ODE solver per particle. So assuming you need like 10,000 particles to get a reasonable result, you need 10,000 instances of an ODE solver, and it quickly explodes. So
yeah, for sure.
And the other thing is that the semi-symbolic method that we are focusing on for ProbZelus, like we like at this point, we have no idea how to derive the math, right? If you have simple conjugate relationships between pairs of random variables, or like you have a tree of things that you know that you will be able to compute a closed form solution, then you can work with that. But if you need to solve an arbitrary ordinary differential equation in the middle of that, that's an entirely open question.
Yeah. Thanks for that small summary, and totally on the go, by the way. I didn't ask Guillaume to prepare for that at all, so well done. And so now that we have the background a bit about this hybrid, this is extremely hard to say as a French person. I'm just going to say hybrid. So hybrid systems. How does ProbZelus differ from other probabilistic programming languages in that respect?
Right. So there are a couple of points here. So one thing is that, as I said, you have inference in the loop. That is a main difference between a general probabilistic programming. Like if you think about Stan, for example, you are defining an entire your program is a model, and the goal is to infer the posterior of this model, right? Here we want to interleave deterministic component with probabilistic component, and there is a possible interaction between them. So think about the tracker model and a controller of a robot, and you want the controller to go somewhere using the estimations. The other thing is that we do need, like we have some constraints, as I said, like we want to execute in bounded memory, and we want to be able to access intermediate results, so that drastically limits the inference algorithms that we are able to use. Like that's why we ended up with SMC. And it's still an open question whether we can explore other things, like and what would be good other options for that.
Yeah.
And the last thing is that we want to be able to check, like in the same line of thought as a synchronous language is, we want to be able to check some constraints. Like we want to be able to check that the program will run in bounded memory. And if you remember, we have this weird runtime where we are trying to do symbolic computation. And this is using a huge dynamic structure that is basically trying to build a Bayesian network at runtime, and try to simplify this Bayesian network as you go and sample some variables if you fail. And checking that this executes in bounded memory is actually tricky. And what we did, and it was mostly Eric Atkinson ideas at the beginning, was to define a static analysis that is able to look at your program and tell you before running it whether it will run in bounded memory or not using our algorithm.
Yeah.
So so that was a very, very interesting work. And the main idea is that you have like, as I said, you are building these Bayesian networks at runtime. And it's possible that you will have infinite paths, like as you go, like you keep adding some random variables, and you want to be sure that at some point you can collect some of the node, like you can remove some of the node from the graph safely, because you have no way to access them anymore. And so you need to define some condition on your program such that this is always true.
Okay.
And of course it's a static analysis, so you have false positive, and I mean, you can guarantee that something will run in bounded memory, but for some programs, they actually run in bounded memory, but we are not able to prove that particularly.
Yeah, damn. That's such a hard use case, because you not only have to worry about the sampling time and the algorithm and just like the efficiency and accuracy of the algorithm, but also the memory load is really something extremely important in this case. Yeah.
There is also something that we didn't touch about that. It's the worst case execution time, which is something really important for embedded systems. And here we haven't started working on that. Like how costly the inference algorithms.
Yeah, I see. Yeah. Yeah, super interesting. And actually, let's try now to dive a bit more concretely now that we have a better idea of the context and the implementation. Can you tell us some real-world applications of ProbZelus and its ability to simulate these systems that you were talking about? Maybe just before that, actually, a distinction that I think we should again make is basically the ability to simulate dynamics in systems with smooth dynamics and systems with discrete dynamics, because I saw it was something also while reading up on the episode that could be important. Is that something that you have? Yeah, can you give us a background about that maybe?
Yeah, so we are in ProbZelus, like we are still in a discrete world. Like we can actually, I shouldn't say that because there is two notions of continuous, right? So when I say we are in a discrete world, it means that we have a discrete notion of time, and at each time step, like you compute streams of values or streams of distributions, but you have a notion of what is the value of each streams at each time step, right?
Okay.
Then you can program your probabilistic models using continuous or discrete distributions. Like this is something you can do. But so far, we need, if you want to do some simulation of, I don't know, like physics or thing like that, you need to discretize it in ProbZelus. That being said, since ProbZelus is built on top of the programming language Zelus, you can express some continuous component and use that as set to generate some observation that you fit to your model. But the model itself needs to be discrete.
Okay, I see.
And so to answer your question about concrete applications, so what we did to play an experiment with ProbZelus is starting with use cases from robotics. And so we had this use case where we wanted to implement a non-trivial robot controller, and so we implemented a linear quadratic regulator, which is known to be optimal for some metrics. And the idea is that we wanted to use a tracker model that is implemented as an HMM, so estimating position from noisy observations at each time step, and feed that to the LQR and see whether you can reach the objective or not. So this was one use case, and we have one other application is that we build a toy version of the SLAM problem, the simultaneous location and mapping problem. So very briefly, like you have an agent that is trying to estimate its position and a map of its environment, right? And in the discrete version, the environment is just a grid that is painted black or white. And the agent can look at its feet and see white or black and move to another cell. And the problem is that the sensor is faulty, so sometimes you see white and the square is actually black. And also you have slippery wheels, so sometimes you say, I want to go up, and you actually stay in place, or go right and stay in place. And given that, you want to estimate both your current position and a view of the map. And the interesting part in ProbZelus is that we were also able to build a simple controller that was trained to explore the part of the map with the most uncertainty first. So because you have this retroaction between the result of the inference and the controller.
Okay. Yeah, this is so nice. Is there any paper or video or tutorials that you can add to the show notes demonstrating that?
Yeah, so the first paper on ProbZelus was published at PLEI in 2020, and in this paper we described the robot example, I think, and the SLAM example. And then in subsequent work, we try to improve the semi-symbolic engine, like moving away from the original algorithm and trying to express more things. And there is another robot example. And so this one was at UPSLA 2022, I think. Where
Okay.
we add some notes.
Yeah, for sure. Like, and add these two ones to the show notes. Pretty sure listeners will appreciate that. And another thing I was really curious about when preparing for your episode was that ProbZelus can be used to prove the absence of bugs in a complex systems, which if I understood correctly. So basically, like trying to prove that there is no bugs in an autopilot of a plane. So did I understood that right? And if yes, how is that possible? Because that's really hard to me to be able to prove a negative.
Yeah, so I don't think this is quite right, but this is an interesting question.
Okay.
So
Yeah, feel free to say I'm wrong. Like I'm wrong a lot of times, so that's no problem.
no, it's not you. It's probably misadvertisement, I guess. But I mean, the motivation for this kind of languages, like putting aside the probabilistic part, is that what you write is really close to the mathematical semantics. So it's really close to the mathematical objects, right?
Okay. Yeah.
And then all the idea behind the work on synchronous languages is that the compilation chain is correct by construction. So what you execute is exactly what you wrote.
Okay.
And for classic synchronous languages, there are some like proof assistants or model checkers that are dedicated to these languages or programs written in these languages, because again, the expressivity is very restricted. So the problem can be a little bit easier. So in some cases, you are able to prove some properties. So not the absence of bug, but you can prove some properties like say, like an alarm will always go on, or you never have buffer overflows or things like that. And so in the same vein, we do have static analysis that guarantee a bunch of stuff, and like the work on the static analysis to prove bounded memory execution is part of that. Like we can prove that there is no bug with respect to execution in bounded memory, but
I see.
that's
Okay.
pretty much.
Okay. But so that would be something that could be tried, that you could try to use to try and see if there is no bug in an autopilot, basically.
Yeah, so there's some work like there is a model checker that is called Kind2 for just like languages, like synchronous languages, and you can try to write your autopilot program, then write the properties that you want to be true for this program, and see if you can automatically prove them. And so check if there are mistakes or not. What we haven't tried is to use that on probabilistic models, and what do we need to do to extend these tools to be able to verify probabilistic models? And like this is an entire new area of research, like doing the kind of work that people do with proof assistant and model checkers, but manipulating probabilities is I think it's fascinating, and I haven't looked at that yet. I know that there is a very recent paper that with the Stan compiler in Coq by Jean-Baptiste Tristan and Joseph Tassarotti at Boston College. So, if people are interested, like, probably something to take.
Yeah, for sure. And again, add that to the show notes because that's definitely something super interesting. And I'm pretty sure listeners will be interested. And if you are, folks, let me know, and I could invite some of the authors of these analyses to the show to do some follow-up episodes.
Yeah.
And so something I like to talk about also is now we have an idea of what ProbZelus is about and what it allows you to do. Now I'm curious about the frontier, basically, of the package, and the challenges and limitations that practitioners will face or are facing right now when working with a language like ProbZelus.
Yeah. So there are actually two questions here, right? As a practitioner, like ProbZelus is a prototype, so you can run example and try to simulate some example on your own laptop, but it's not at a state where you can embed the code. And actually, I come from the community of programming language design and semantics and stuff like that. And the low-level aspects of what you need to do to output low-level code is not something that we focused that much. And so right now the prototype is emitting OCaml code, so it's relatively high level. And there is still a lot of work to do from going from OCaml to a low-level C or Rust or whatever code that you want to embed.
I see.
So so what we wanted to do is to have something to be able to do some experiments and prove some ideas and see what we were able to express. So it's not something that you can already use to program your embedded system. That being said, like a lot of ideas, that originated from our team and mostly from Marc Pouzet when he was working on Lustre and Lucid Synchron and then Zelus, were adopted by ANSYS. And there is an industrial tool that is called SCADE that is used, for example, at Airbus to program airplane controller, but not with the probabilistic part, of course.
Okay.
And for researcher, I think that there are a lot of interesting questions. So one thing that was really tricky for us was to define the semantics of the language. So what are the mathematical objects that you manipulate with the language? Because we have this, we have two things, right? We have this notion of streams, and you want to be able to combine streams inside the probabilistic world. So what does that even mean? And you want to add this inference in the loop. So what does that mean to look at intermediate results? Right? So defining the semantic was tricky, so that's one point. And then the restrictions that we have because of the settings are also imposing new constraints. So the main example is bounded resources.
Yeah, so like definitely something that will be on the roadmap for a long time. Yeah.
And the last thing I wanted to say is for practitioners is one thing that is very tricky is to convince people that it's actually useful, because embedded system designers, they are used to uncertainty, right? We do have airplanes everywhere that are flying around, and they do evolve in an uncertain world with noisy environments. They do encounter birds sometimes, and they have to react to that. So how did they do that? And the answer is that they are manually coding some stochastic controllers that are proved to be safe on pen and paper, but they are deriving the equation by hand and they are programming that, right? So if you talk to an embedded system designer, they are used to, say, Kalman filters, for example. They know how to implement that.
Yeah.
They say this is all I need to estimate a position, and I know how to derive the equation. So why should I write the probabilistic models? And the point we want to make is that by making the underlying probabilistic model completely explicit, you make explicit all your assumptions about the environment, and that's actually better and easier to modify, and it's more modular and so on.
Yeah. I mean, that's interesting because it's also a general remark, I would say, about Bayesian statistics, right? It is definitely something I have to say a lot also in a lot of my courses and teachings and consulting work, where it's definitely a lot of this. Why would that kind of method be useful? Which is a good question. I mean, I like that question. And yeah, usually the explicit modeling and explicitation of your priors, which are just assumptions, to me is something that makes that framework really powerful.
Yeah, and the other thing is that sometimes it's difficult to, I mean, it's like there is a step that people need to make when they are trying to use Bayesian methods, right? They need to think about the generative process and stuff like that, and it's not completely natural, at least for some people, and it's difficult to convince them that it's actually better than writing the solution. And I mean, the Kalman filter is a perfect example because you can always say, "Oh, but you are already doing that." Like it's it's just the same direction.
Yeah, no, for sure. That's always something that really interests me. And actually, talking about that, teachings and things like that, you quote out again, really hard to say for French people. Quote a class on probabilistic programming languages in France at the École Normale Supérieure, which I found super interesting because first, I don't know how new PPLs are in the curriculum, but as a very old person in my university years, so beginning of the 2010s, Bayesian statistics was absolutely not taught at the university level like that, with that kind of courses that you did really in depth and going into probabilistic programming languages and so on. So first, I'm super happy about that. It's super cool. So yeah, like I'm curious just in general about that course. First, because does that mean that you find that Bayesian statistics and probabilistic programming languages are getting more traction at the university level, at least in France? And second, you taught it from the perspective of programming language research. So I'm curious about the key takeaways or insights that you gained from teaching this, to me, quite unique angle.
Yeah, so that's great questions. So this started when I went back to France. So I was contacted by Christine Tasson, who was working on probabilistic programming, but from a really semantics point of view, like denotational semantics and category theory and stuff like that. And she wanted to build a proposal for a course at MPRI, so it's a Parisian Master for Research in Computer Science, I would say, something like that. Maybe there is an official acronym in English, I should say. Yeah, so it's not only ENS student, they're also from Paris 7 University, or it's not Paris 7 anymore, it's Paris Cité University and Polytechnique and Paris Saclay and people from all background, but these are students with a very strong background in the theoretical computer science and mathematics. And so the emphasis for the course was really to do something that was in the middle between practical implementation and semantics and denotational semantics, typing, category theory, and programming language theory. So I think it got accepted, like the proposal got accepted because probabilistic programming is getting more and more traction. And you can see like there is a boom in the number of published papers on the topic. So that must have been one reason. And the other thing is that there were other courses that were teaching a little bit of probabilistic programming. Like, for example, there is a probabilistic lambda calculus or another course on denotational semantics that were presenting this probabilistic programming as a use case or not really a use case, but a part of the course. And what we wanted to do is to propose something that was really focused on Bayesian inference. And how do you reason about that? And so for the second question, it was interesting. So the idea was to divide the course between Christine and me. So Christine was doing the denotational semantics and like a really abstract formal part of the course. And I really wanted to give the student a taste of how can you implement these things and what can we use from probabilistic, from programming language theory that can help us. And so, for example, this includes like building a type system for a probabilistic language, and then how to use functional programming to implement your own runtime libraries with your own inference algorithms and things like that, and progressively adding more and more to the language design. And yeah, and the last thing is that we wanted to give them a taste of a lot of different probabilistic programming languages. And so we try to build some labs that are using a lot of different flavor of probabilistic languages. So like Stan, Pyro. It's not PyMC yet, but
Not PyMC.
maybe
What's up?
Maybe later. I did use an example from the Bayesian methods for hackers. It was written in PyMC.
Yeah.
But it was for the first course, so I wanted them to implement that in their own PPL. So.
Yeah, I see. Nice, that's super cool. And of course, like if you need any help for PyMC examples, feel free to reach out. I will be happy to help. As long as the program is not written in French, because I cannot code in French.
It's not in French.
Yeah, no, that's super cool. And so, who is the audience of that course? What level are they, and what are they studying as a major?
Right, so it's a second year of master, and it's a master where a student can choose whatever they want in a relatively huge set of different courses. But most people that were attending the course were focusing on like functional programming, static analysis, programming language semantics, and things like that. And so there was a lot of efforts at the beginning of the course was to explain what is Bayesian inference and why does it work backward compared to what we are used to. And this is why I said like it's there is a gap. Like you need to cross that gap, and it's not obvious for a lot of people. Like how does that work, and why are we asking questions about outputs, and who is giving us this output for the program?
Oh, yeah, I see. And is that one of the main difficulties you saw that students were having?
Oh, that's one difficulty, and so really understanding what is inference, like what is Bayesian inference. Another difficulty is that what is the difference between like just a Bayesian model where you have your prior and then you do some observations and you extract the posterior, and probabilistic programming, which is basically like Bayesian modeling but on steroids, right? Because you can write a probabilistic program that has no inputs and that computes a really weird distribution using Bayesian inference, and it's not like the classic coin example, right? So there is no real notion of inputs, outputs, but you can still use these objects and define weird model. And the question then is, can we give a precise mathematical sense to this kind of objects? What is it, and how can we manipulate them? And so this is one difficulty, and the second difficulty is that the semantics that we present are based on measure theory, and it's not completely the case right now, but it's still not something that is heavily studied in France, and it's possible to go around it, right, in your curriculum. When I was growing up, I think I had one course about measure theory, in my undergrad, and that was it. Like it was really a black hole.
Yeah.
No, it's not the case anymore, but for some of the students, it's something that they have relatively little knowledge about. So that
Yeah.
can also be tricky.
Mm-hmm. Yeah, for sure. I can understand that. And so when I'm wondering if there is one main thing that you want to adapt for next semester or next year and the next time that you're going to teach that course based on that feedback that you already got from the first iteration.
That's a very good question. I haven't thought about that at all. Uh, One thing that I want to adapt for sure is project. So we typically give a project every year, and I want the student to be confronted to this notion of inference and inference algorithm relatively early in the course, and so I want them to try to program it as early as possible.
Mm-hmm.
And I would like to, yeah, I want them to have a connection between this kind of inference algorithm and what is really implemented in practice in actual programming languages like PyMC or Pyro or Edwards or thing like that.
Yeah.
And so last year it was really like implement whatever inference you want and try that on a simple model. And I want to do something more guided and maybe a little bit more advanced this year.
Nice. Okay. Well, interesting. Really curious about how that will go. So now that we, so almost at the end of the show, so let's kind of de-zoom a bit. And I'm curious, in your opinion, what are the most exciting developments that you see in the field of probabilistic programming languages?
Yeah, that's a very good question because it's a really active field, like in many different directions. So I will probably focus on a few of them, but one thing is that all these new advances on the inference front, and so there are these things, a lot of work about synthesizing variational guides from your program automatically. Like if you think about the Pyro language, at the beginning you needed to write by hand your inference guide, and it was looking really similar most of the time to the model, at least for basic usage. And they had this zoo of auto guides that they implemented like relatively recently, like 1 or 2 years ago, where they started to try to automatically synthesize some guides. And there are some new works about that are published even like this year, using programming language theory to improve the synthesis process for that. So this is really interesting, and this is to be put aside with this new normalizing flow variational inference, where you can do you can have amazing results with that. So I think this is really exciting. I really want to know more about that. The other thing is that for the practitioner, there is this entire line of work about the Bayesian workflow, where the question is, okay, you have your probabilistic models, but how do you come up with that? Like, and what do you need to be able to iterate over your models to do better approximations and better inference and stuff like that? And I think this raises a lot of very interesting questions for language design. So what can you do to help programmer with this kind of workflow? That's for me. It's for me as a programming language designer. This is really interesting.
Yeah.
And finally, for the semantics, like on the abstract level, there is all these works about the new quasi-Borel spaces and probabilistic cones, where people are trying to define measure and sigma algebras over very weird set, like a higher order function and things like that. And this line of work is fascinating, and
Yeah, agreed. Definitely some good stuff ahead. Yeah, and actually, if we now go back to ProbZelus a bit, if you look ahead, I'm curious what future directions or research areas you see for ProbZelus and its integration into practical systems or industries.
Yeah. So on a research point of view, we are still actively working on inference techniques and static analysis around ProbZelus. But there is one thing that I think is very promising is the like leveraging the compiler chain for probabilistic models. And what I mean by that is that if you are able, for instance, consider the Kalman filter again, because this is like the paradigmatic example for us. Like, you know that there is an exact solution and you are able to compute it right. So what if the compiler was able to compute the exact solution for you and generate the code? So if you are able to do that, you don't need to embed the inference engine anymore. And so you can just run the deterministic code, even though you are still working with probabilistic model. And so now the question is, can we do that for other models? Like, and how far can we go? And can we bound the number of resources that we are willing to embed and still get some good results, some good approximation results? And what kind of static analysis can we do on this kind of models? So.
I see. Yeah, that'd be cool indeed. Okay, cool. Well, before we close up the show, I could still ask you a lot of questions, but I want to be mindful of your time. So, is there a topic I didn't ask you about, but that you'd like to mention?
No, I think it's
Great.
we covered pretty much everything.
Cool. So that was my challenge. So apparently I did it well. So awesome. Well, Guillaume, before stopping the recording, I have to ask you the last two questions I ask every guest at the end of the show. So first one, if you had unlimited time and resources, which problem would you try to solve?
Yeah. So this is a really difficult question for me because I'm not really good at selecting projects and driving people around that. And so I will give a partial answer, which is I really like the French academic system where it's only partly based on the grants, right? So you have a lot of people that can work on whatever they want. And I really like this idea. And I think there is a lot of huge progress that were made because people were working on very strange areas of research. Right? So what I would do if I had infinite resources is that I would give like a fraction of these infinite resources to a lot of bright people and say, you can work on whatever you want. And hopefully this will help to solve some of the big problems in the future. The trick is that a fraction of infinite is still a lot, so I'm glad that I can do with that.
Yeah, that makes sense. And second question, if you could have dinner with any great scientific mind, dead, alive, or fictional, who would it be?
Yeah. So again, I'm not great with social events, so a dinner is a really stressful event for me. Like you just have one dinner, like you need to make it right. But then again, I am fascinating with origin stories, and I would really like to combine people that can interact together and see how they can exchange their views on different stuff. So I would really love to have a dinner with John von Neumann and Grace Hopper. So like the first compiler with the first computer designer, and then add John Bacchus for the first high-level programming language designer, and see how they interact and what kind of ideas they can exchange, and if that would have changed something in their design, like
Yeah.
So you start from a very high level. Like if you think about curriculums right now in computer science, you really start from very high level programming languages, and you typically go down to the chain. And history was the opposite, right? We started from really low level stuff and building from them. So what would have been different? I think that would make a great dinner.
Yeah.
At least for me.
Yeah, that does sound good. I agree. Awesome. Well, Guillaume, thanks a lot. That I really learned a lot. That was really an original topic in an episode. So thanks a lot about all of that and diving into all the details. As
Thank you
usual,
very much.
we'll put resources and a link to your website in the show notes for those who want to dig deeper. Thank you again, Guillaume, for taking the time and being on this show.
Thanks.
Let me show you how to be a good breezy and change your predictions after